Hello, everybody. Welcome to our seminar. Today, we have the pleasure of having Mykhaylo Shkolnikov. Misha earned his PhD in mathematics from Stanford University in 2012, and before joining Carnegie Mellon University as a full professor, he was an associate professor at Orphy in Princeton. Misha is the recipient of the 2018 Erlang Prize by the Informs and of the 2019 Early Career Prize by the SIAM Activity Group. He serves as an associate editor for Analysis of Applied Probability and Applied Mathematical Finance and Mathematical Finance. His research interests include stochastic portfolio theory, stochastic partial differential equations, random matrices, and models of random growth. Today, he will be talking about pathwise entropy solution of SPDEs via rank-based models with common noise. Thank you very much for giving this talk, and the floor is yours.
Thanks a lot, Ibrahim. So thanks for this opportunity to speak here. I was actually not sure the seminar is still ongoing after the pandemic, so I'm glad that it keeps going strong. So I'll talk a bit today about some recent work with my postdoc here at CMU, Lane Chun Yeung, who I think is in attendance today as well. And so this paper is supposed to appear on arXiv within a week or two. And so what I'll be discussing is the limit of certain kind of models from stochastic portfolio theory, known as rank-based models with common noise, when the size of the market becomes large. So, the meaning of all these terms will become clear as we go along. So I'll briefly describe the motivation and kind of the starting point of this work first, and then, as you will see, I'll have to introduce a bunch of things. So on the one hand, I'll describe how we think about the capital distribution in equity markets in stochastic portfolio theory. On the other hand, I'll introduce you to a notion of solution of SPDEs known as Pathwise Entropy solutions. So that's something that Leon's, Perthame, and Souganidis have introduced a couple of years ago. And then the main result will bring these two things together and will explain that these pathwise entropy solutions actually do arise in stochastic portfolio theory as limits of large markets. And if there is time in the end, I'll say a few words about the proof, but let's see how far we get. So the starting point for this project for me was a very nice paper by Gess and Souganidis, which appeared in SPA in 2017. And so that paper is concerned with the stochastic PDE in the second line of the slide. So it has nothing to do with finance, it's purely analytic or probabilistic paper. And so what they were interested in was to make sense of a solution to the equation that you see here for U. So let me first maybe parse through the equation to explain, what its various aspects are and why it is interesting. So first, imagine that we set G to 0. So we kind of drop the noise term here and just keep the part in front of the dt, right? So if we do that, and if I just move dt to the left-hand side, I end up with a PDE, right? So the time derivative of U will be given by some kind of elliptic, nonlinear elliptic operator applied to U. And this PDE is actually quite well known under the name porous medium equation. And so what it describes in mathematical physics is how liquids propagate through porous media. So something like water through the soil. Okay, so if you look at the SPDE without the noise, so with G equal to 0, you end up with the porous medium equation, which is quite a well-known object in mathematical physics and has some interesting properties, such as finite speed of propagation, for example, for certain choices of sigma. So there is interest in this equation that's in its own right. And this equation has also appeared in my own work as a limiting equation for a large financial market. And so when I saw the Gess and Souganidis paper, I was naturally curious if the full equation, so the full SPDE in the second line, is also describing some kind of large market limit that would be relevant in stochastic portfolio theory, right? And so before I move on, let me comment on the noise part in the equation as well. So if we instead kind of drop everything in front of dt and just keep the g dw term here, then you end up with a transport type equation, so first order hyperbolic PDE. And so if w was some kind of smooth signal of time, we would be just transporting the solution along the trajectories of w, right? So what Gess and Souganidis were interested in was to understand what happens when you have both of these effects. So you have the transport part and the diffusive or parabolic part. And they're interested in defining the appropriate notion of solution for this kind of equations. So I'll come back to the equation a little bit later. But before that, let me set the stage kind of from the financial perspective. Okay, so in stochastic portfolio theory, what we're interested in, among other things, is the distribution of capital among companies and its implication for the investment in portfolios in those companies and their stocks. And so what you see here is kind of the typical picture in the beginning of every stochastic portfolio theory talk, right? So what you see are the so-called capital distribution curves. So each given curve here gives you a snapshot of the public market in the US from largest company to the smallest in terms of the market cap. So currently Microsoft is the largest, and it would start, I think, somewhere between 1% and 2%. So, roughly 1.5 or so percent of the US equity market cap is invested in Microsoft. And then you sort of go down from the largest company to the smallest. And so for the later years in this plot, roughly 5,000 largest companies in the US are plotted, right? And so what you see in this picture is that the curve is kind of stable over time, especially its top parts of the larger companies. And you also see kind of a linear decay of the curve, which translates into a power law decay of the market weights. And there is a lot of literature, in particular in economics, about why that is, so why you get this power. All right, so kind of from the math finance perspective, what you would like to have is a mathematical model which is able to capture the picture that you saw. And so still to date, the simplest model that we have to capture this picture is the rank-based model introduced by Bana, Fernholz, and Karatzis about 20 years ago. So the model is given by the SD in the second line. So it's very simple in a way. So for each company, we are taking the log of its market cap to get a real valued variable instead of a positive one. And we drive it by its own Brownian motion, BI, and make the two coefficients, so the growth rate of the company and its volatility, just dependent on the rank. And that's the only quantity it depends on. And the rank is written here in terms of the empirical measure. So I write nu and t for the empirical measure of the market. So I put weights of 1 over n at the locations of the log caps. F is the corresponding CDF. And so if I evaluate that quantity on xi, I will get some number of the form k over n, where k is the rank from the bottom. Okay, so we have this rank-based dynamic. And the reason it's useful for capturing the picture in the previous slide is that if I write the ranked market weights in terms of the ranked market caps, I get the formula in the second bullet point. And the right-hand side of this formula involves the ranks or the order statistics of the xi's, and those form a reflected Brownian motion. So the key property of this model is that you get a Markov process for the order statistics of the xi's. And it's in fact a very well-known and well-studied Markov process, a reflected Brownian motion. So we can actually say quite a few things about the stationary distribution of this process. And in particular, we can calibrate the stationary distribution to the picture that we see here, right? So what you would do, you would choose some class of coefficients B and sigma such that the stationary distribution of the corresponding market weights fits, let's say, the average curve that you see here, or typical curve that you see here in some sense. So somehow the model captures the static behavior of the market perfectly, right? So you can perfectly calibrate to the typical capital distribution curve. But of course, for investment questions, you're actually interested in the dynamic behavior, right? So you want to actually know how these curves fluctuate over time. And so what that means for your portfolio, so how you should rebalance between those different companies. And so understanding the dynamic behavior is quite a bit more complicated. And so about 10 years ago, more or less concurrently in my own PhD thesis and in a very nice work by Jourdain and Rainier, we have suggested to look at the n to infinity limit to understand the dynamic behavior, right? So since we're anyway thinking about institutional investors in this context, and they invest in hundreds or even thousands of these companies, the number n of companies is large, so you can try to take n to infinity and try to get something more tractable than the original high-dimensional one. And so in our original work, what we looked at is the n to infinity limits of the market as encoded by the CDF. So you take the CDF of the empirical measure, so that's this f of nu n object in the second line. So that completely describes how the capital is distributed at different times. And you take the limit of that, and you end up with a PDE, which is exactly the porous medium equation which we had on the motivation slide. And there is a very simple connection between the coefficients here. So the capital B that you see here is just the antiderivative of the little b. So it's the aggregate growth rate up to a certain rank. And sigma, capital sigma here is the antiderivative of 1/2 little sigma squared. So you look at basically the variance associated with the volatility in your model. And again, you aggregate up to a certain rank. This is your capital sigma. So these are the two nonlinearities in the PDE that you got. Now, what you would hope to do is somehow to approximate what happens before the limit, so the f nu n by u. But of course, you cannot hope to get a satisfactory approximation here because the dynamics for you is deterministic, right? So you're trying to approximate the random fluctuations in your market by something deterministic. And so, that's just not good enough. So the next thing you might try is to get the central limit theorem. So to study the fluctuations about this deterministic limit. And that's something we did with my PhD student, Praveen Kohli, 6 years ago. And so you can indeed do that. So you can prove a central limit theorem. The scaling is root n, as kind of typical for mean field models. And so if you subtract the law of large numbers, rescale correctly, you converge to some sort of random limit. And it's not too important what the equation for G is for our discussion today. So let me just say that G solves, again, some stochastic PDE, and in fact, a very simple one, which has a Gaussian solution. So G will be a Gaussian random field, and it's not hard to determine its mean and covariance parameters. So you have fairly tractable object in the central limit theorem, right? And so kind of putting everything together up to that point, you arrive at the approximation of the actual market, so of the market in the rank-based model, by the sum of u and 1 over root n times g, right? So that's kind of the central limit approximation that we had up to that point. And so we went on to test it at Intech back in 2018 or 19. And so essentially what we found was that if n is large, but not too large, so roughly on the order of 100 or a few hundred companies, this approximation is actually working quite well. So you can calibrate to what is happening in the actual US stock market. But if n becomes much larger, so think of 1,000 or a couple of thousand companies, then the approximation starts to break down. So you cannot successfully calibrate. And that's because you have this factor of 1 over root n in front of g, which means that you still have somehow fairly little noise in your approximation, so little randomness when n is too large. And so, okay, so then if you think about this, it's of course typical for mean field models that because of the propagation of chaos phenomenon, the noise disappears and becomes small as n increases. And sort of the typical remedy for this is to introduce common noise, right? So to introduce noise or randomness that's common to the different components or particles, which will survive the n to infinity limit and give you an order 1 randomness in the limiting dynamics, right? So, even back then, 6 years ago, kind of we thought of this model in the middle of the slide where you introduce a common noise, a common Brownian motion W, now driving all the log caps in your market, and you put, again, a rank-based coefficient in front of that. So that's the gamma part that you see in front of DW. And so the reason for the rank-based nature of this coefficient is that you still want to get something tractable for the order statistics of the xi. And so if you put a rank-based coefficient, if I rank or order the xi's, I still end up with a reflected Brownian motion. So that's, again, a very tractable process that I can calibrate to the typical capital distribution curve. So somehow the typical or the static behavior I can, again, calibrate to with this kind of model. And so now the question is, can you still say something sensible about the dynamics of this model? And again, to make things more tractable, we will send n to infinity as we did without the common noise, right? And I should also mention that kind of for simplicity, both here and in the paper, we have just one common Brownian motion, but exactly the same analysis applies for any finite number of W's. So if you're actually interested in calibrating these kind of models, you will probably want to use more than one factor. And so you can do that. And the analysis I will describe will still apply. So if you have a sum over some j, let's say, of gamma j dwj, and you have a finite number of these factors, maybe 3, 4, 5, the same analysis will still apply. All right, so that's kind of where we're headed. So we want to understand the large n limits of this model. And this is where we will exactly see the pathwise entropy solutions of Gess and Souganidis showing up. Right, so what you can do is first run the usual Mykhaylo heuristics. So the model is of mean field type, right? So all coefficients in my model depend just on the empirical measure and the underlying particle. So I can sort of guess how the limit will look like as I send n to infinity. And so on the level of the CDF, the limiting equation is what you see here in the second line, and that's precisely the SPD studied by Gess and Souganidis. Okay, and so to kind of set up, to set the stage for our main result, let me explain how they managed to solve this SPD or define the notion of solution, and say a few words about this concept of pathwise entropy solutions in the Gess and Souganidis paper. Right, and so those, I should mention, go back originally to the work by Lyons, Perthame, and Souganidis. And that original work was concerned with the hyperbolic case, so essentially with the case where there is no dt part. And then there was a follow-up work where they had a parabolic part in front of dt, but less general than here. And then the Gess and Souganidis papers, sort of exactly the setting that we're interested in here. Okay, so how do you make sense of this equation? So what they do is the following. So you introduce an auxiliary variable psi, which in our case will stand for the rank, right? So it will be a variable between 0 and 1. And if it is 1/2, it means that your current log cap so your company is exactly in the middle of the market, meaning that exactly half of the capital in the US stock market is invested in larger companies than you, and exactly half is invested in companies that are smaller than you. Okay, so that's the role of psi. And so what you do, you define this indicator function where you just threshold your solution U. So you set it to 1 if you're above psi, to 0 if you're below psi, right? So for any fixed psi. Okay, and then what you do, you sort of naively or courageously, depending on how you see it, apply Ito formula to this indicator, right? So if you apply Ito formula to this indicator, you end up with the equation at the bottom of the slide. And yeah, let me sort of parse it carefully. It turns out to be not such a bad equation for this chi object, right? So if you look on the left-hand side, in terms of chi, what we see here is just a linear parabolic equation on the left. And then you have a source on the right, which is also not too bad, right? So the long parentheses inside of the d psi is some measure, right? So we're taking one derivative of a measure, so it's a distribution, but okay, it's not so terrible because it will be a source for a parabolic PDE, which has regularizing properties. The more problematic part in this equation is the drift, so the coefficient in front of the first derivative of chi on the left, because W prime, so the derivative of the driving noise, will appear in that coefficient. And so for us, W is a Brownian motion, so W prime is white noise. So we have to think about somehow equations where you have a distribution value to white noise value drift, which is something that people have looked at actually among other places in fluid dynamics, but let me not detour there. So it's sort of a problematic term that you have to carefully address. And so in this concept, in this context, what Gess and Souganidis suggest is to think about the weak formulation of the equation for chi, so testing chi against test functions, but kind of the clever idea is to use very carefully chosen test functions to test against, so not just any smooth function. And so these kind of carefully chosen test functions are these functions rho that you see in the current slide. So they are themselves defined as solutions to a transport equation, but maybe for the purposes of the talk, it's actually more instructive to look at the explicit formula, right? So in the middle of the slide, you see a formula for rho, where we will let rho 0 vary over all smooth test functions, but the arguments of rho 0 will be chosen in this very careful way as functions of tx and psi. Okay, and so if you do that, and you test your indicator chi against this, very particular type of test functions, you will end up with the weak formulation at the bottom of the slide. And kind of the miracle that happens here is that the W prime has disappeared from the equation, right? So the reason that happens is that we are, in a sense, looking at the weak notion of the time derivative of chi times rho. And so kind of in that time derivative, if you write it out, the W prime is hiding. So it's sort of hidden in the weak formulation of the first term. So the first term somehow implicitly hides the W prime that you saw on the previous slide, right? And so you end up, all in all, with some equation which now looks pretty reasonable, right? So chi is a function, so you can integrate it against rho. So the first term should make sense. The second term, you're integrating chi against rho xx, so that's still a smooth function. So that should also make sense. And then in the last term, the derivative in psi is moved to rho again. So again, you have some nice smooth function integrated against the measure. So that's also a well-defined object. So overall, you end up with a formulation of the SPD where all the bad terms have disappeared. And so you can use that as a definition of your solution, right? So at the end of the day, Gess and Souganidis define their notion of solution called pathwise entropy as random fields U that in essence satisfy the equation in point B. So that's exactly the weak formulation I was just discussing. And on top of that, they impose two regularity assumptions. So this is what A and C are about. So A, in essence, imposes that Ux is square integrable in T and X. So think of U again as a CDF. So this assumption says that the CDF, or the measure underlying the CDF actually has a density with some integrability. So it's kind of a mild regularity assumption here. And in C, what looks like some kind of integration by parts is in fact also a regularity condition in disguise. So let me try to explain that. So let's look at the left-hand side in C. So on the left-hand side, we're trying to integrate rho x against chi. Don't worry about sigma too much here. And so, one way, so if chi and rho are nice functions, one way to evaluate this integral is to integrate by parts and move the x derivative to chi. However, chi is in fact an indicator, right? So it's the indicator that you see in the bottom line. And so if I move the x derivative, I will get the x derivative of the indicator that U is bigger than psi. But, as before, let's be courageous and just differentiate this indicator. So what will we get? Intuitively speaking, right? So if you differentiate this indicator, what we should get is a direct mass at psi evaluated on U times Ux, right? If you apply the chain rule. And so if I just plug in, so if I move the x derivative on the left-hand side to chi, and I plug in direct mass at psi evaluated on U, Ux, and I integrate, so I can integrate out the direct mass, and I will end up with the integral on the right-hand side. Okay, so what this third condition is saying is that this manipulation with the indicator, moving from the indicator to the direct mass, that it's actually a valid kind of manipulation, which really has to do with the regularity of U here. So it's kind of a hidden regularity assumption on U. Okay, now
ask a question here.
Yes.
So in this definition, all the rows are within the class that you defined in the previous.
Exactly. So these are the same rows. So that you see in the middle of the slide here. So it's some nice test function rho 0 evaluated kind of on a carefully chosen argument.
Thank you very much.
You're welcome. All right, so these three properties define what's called the pathwise entropy solution. And I guess maybe it's worth mentioning here that the main result of the Gess-Souganidis paper is to show that there is a unique pathwise entropy solution for this SPD under suitable assumptions on the coefficients. And so in particular, it means that the three properties A, B, and C uniquely characterize my random field U. And so we can build upon that. So with Lane, what we proved was that if you take a rank-based model with common noise, as previously discussed, and if you look at the CDF in that model, it will converge precisely to this unique pathwise entropy solution of the Gess and Souganidis, right? And so again, there is a simple correspondence between the coefficients. So capital B is again the aggregate growth rate up to a certain rank. Aggregate sigma is capital sigma is the aggregate variance sigma squared up to a certain rank divided by 2. And capital G is the aggregate common noise volatility up to a certain rank. Okay, so that's the main result. And since I have some time left, let me say a little bit about the proof. Okay, so let me try to give you a proof sketch. So kind of the main difficulty in proving this result is to show that any limit point of my markets really forms a pathwise entropy solution. And it's not completely obvious because the pathwise entropy formulation is not so convenient for taking limits, right? So in particular, various things here. So the two regularity properties, A and C, for example, they just don't hold before you take the limit. So, you know, if you wanted to kind of tackle the problem directly, you would have to come up with sort of approximate versions of all these three properties for the actual market, so for the fixed end model. And that seemed like a difficult task to us. So maybe it's possible, but certainly not trivial. And so in fact, we took a different route. Namely, we actually decided to work with the martingale problem for the limiting SPDE, which from the probabilistic perspective is anyway a bit more natural than the more analytic pathwise entropy solution. So what is the martingale problem? So you first write down the Ito formulation of the stochastic PDE from before. So that brings about this new coefficient gamma, which is the antiderivative of gamma squared over 2. So that comes from kind of this Stratonovich to Ito transformation. Okay. And then what you do, you can test your U now against arbitrary test functions phi, let's say, of x. And so if you do that, you see, because of the form of the equation, you can move all the derivatives onto phi. And so you can write down kind of a natural martingale problem, right? So you take the integral of u against phi from the left, you subtract all the dt terms that you find on the right, and you impose that that is a martingale for all suitable, so smooth enough test functions phi, right? And on top of that, you need to specify the cross correlation across different phis, but you can do that. So you come up with a martingale problem for the SPD. And in fact, it's now not hard to see that if I take the n to infinity limit of my model, my limit will have to solve the martingale problem. So the crux of the proof is then to show that, in fact, any solution of the martingale problem is automatically a pathwise entropy solution. And so if I can do that, then I can leverage the uniqueness result of Gess and Souganidis and get my law of large numbers. So I can get the pathwise entropy solution as my limit. Okay, so I'll explain this implication in just a moment. Let me go there first, actually. Okay, so kind of the crux of the proof is this implication martingale problem to pathwise entropy. And what that means is that we have to verify for any solution of the martingale problem, the three defining properties A, B, and C of the pathwise entropy solution. So the three bullet points on the slide, they kind of give a hint of how we address each one of them. Okay, so let me start with the first one. So first, you need to establish some a priori regularity of your solution. So I want to say that, in fact, any solution of the martingale problem will have a density Ux that is an L2. And you can just ignore the sigma because we assume that to be bounded anyway. So it's really about Ux plus. Okay, so this might seem like a difficult problem because in the absence of the common noise, so if the dW term was not there, at least I'm aware of only one proof of this type of regularity for kind of general McKinley-Lassov type equations. And that's the proof by Gärtner that builds on some non-trivial construction of Krylov. and sort of requires somewhat heavy machinery. So a certain convexity construction that Krylov came up with in the context of parabolic PDEs. Now, it turns out that in this case where you have the noise, things actually simpler. So there is actually a simpler proof for this regularity that we could give here. And so here is how it goes. So the key idea is to apply Ito's formula to U squared, right? So at least heuristically speaking, so you have some SD for U that you see here. So I can compute du. Okay, so at least heuristically, I can do that using Ito's formula. Okay, and so what's the benefit of that? So the benefit is that on the left-hand side, I will have something fairly tractable, right? So we'll have just U squared. So I can, for example, integrate it over T and X and, you know, get estimates on this quantity. And notice that it does not involve UX, right? So it's about U, which is the CDF. And so that's an object that's much easier to estimate. So for example, it's bounded. So locally, it's automatically as integrable as you like. Okay, so what do I get on the right-hand side if I apply Ito's formula to U squared? Well, I will get 2U du. So essentially, I will have all of these terms in front of dt multiplied by U. And then, okay, some extra stuff, but let me focus on that term. So I'll have whatever sits in front of dt here times U. Okay, but now I integrate in T and X. So essentially, I have some second derivatives of U integrated against U, right? So if my equation was linear, if sigma and gamma were identity, I had just UXX. The term I would get on the right-hand side would be UXX times U integrated. Now, if you integrate this guy, you can naturally integrate it by parts and get exactly the object we're interested in, namely UX squared, right? So that's the object we're trying to estimate. And so kind of the magical thing that happens here is that the Ito correction term that you will get when you apply Ito's formula to U squared will actually cancel out some of that UX squared term. So you will have, you know, some integral of UX squared with the correct sign on the right-hand side left, essentially, and just the integral of U squared on the left. So you'll be able to estimate UX squared, its L2 norm, in terms of integrals of just U squared. And so that's much easier. And so, yeah, so then you're essentially done. So it's not so hard. Basically, you just need some tail estimate on U, on the CDF, and you'll be done. Okay, so that's how we get this regularity. So then we prove the second bullet point, so kind of the defining property of pathwise entropy solutions that you see here. So this is, again, the weak formulation of the SPDE when you integrate against these cleverly chosen test functions, rho. Okay, and so at least to me, it was interesting to anyway understand where this equation comes from, and so to get a probabilistic perspective on it, and you're sort of forced to do that in the step anyway. Is there a question? Oh, yeah. Okay, and so it turns out that, right, so what this complicated logic equation ends up being is simply another application of Ito's formula. And so what you have to do is take rho. So here, this rho zero thing is just the explicit formula for rho, and you just integrate it in the rank variable up to U. And so if you apply Ito's formula to this quantity, what comes out is exactly the pathwise entropy formulation. So in essence, that's sort of the probabilistic meaning of this formulation. So the probabilistic meaning is that if you apply Ito's formula to the quantity integral 0 to U of rho 0, things are chosen in such a way that you will cancel out W prime, and you will have kind of only nice terms appearing in this Ito formula. So that's in essence exactly the pathwise entropy trick of Lyon's, Perthame, and Souganidis, but kind of formulated in a more probabilistic way. Okay, so you got the second property, and then you're just left with the last regularity property, so property C that you have in the last bullet point. And so kind of here, the key idea is to use the core area formula. So essentially, if you look at the right-hand side first, you have, roughly speaking, a function of u times ux dx, right? And so that sort of suggests that you should introduce a new variable xi being equal to u. And so when you change variables in this integral, this will get rid of this ux dx term. So the ux will disappear. And so that's pretty much what this formula is saying. And so formally, to justify this change of variables, one way to do it is to use the core area formula. And kind of the key to apply that is that you need to know that you have a continuous CDF U. So in this one-dimensional case, that's exactly the regularity that you need to justify this equation. And so once you have the first bullet point, so once ux is square integrable, you actually automatically have a continuous CDF, at least for almost every t. And so that allows you to justify the last regularity condition for almost every t, and that's enough. So it turns out that you can, so it's enough to have this regularity for almost every t, and the whole Gess-Souganidis machinery goes through. So it's enough to verify it just for almost every t here. Okay, and once you have that, you have shown that every solution of the martingale problem is a pathwise entropy solution. You use uniqueness, and you get your law of large numbers. So before I finish, let me just quickly come back to the main theorem and explain how I envision people actually using it, right? So in terms of the financial context, right? So what one would hope is that the limiting equation, so the SPD, is somehow more tractable than the high-dimensional SD in the rank-based model with the common noise. And so, right, so what I envision going forward is that you can use this SPD to actually understand how portfolios perform in large rank-based models. And so without the common noise, we managed to do that. So, there is a paper that I wrote with Sergio Almada Monter and Cha-Cheng Zhang about 5 years ago, which kind of built on the central limit theorem we had without the common noise and provided estimates on portfolio performance using the limiting equation. So I can imagine that one can do the same type of thing with this limiting SPD. A different route is to do numerics, right? So computationally, you can try to numerically solve this SPD, for example, using a finite difference scheme, and then calibrate it to the actual capital distribution curves that you observe, and then kind of use that calibrated approximation of this SPD as your model to study portfolios, right? So for example, to test the performance of certain portfolios that you want to try. So that's how I envision the use of this result in finance, but that's left for future work. For now, and we'll just provide the theoretical foundation in this joint work with Lane. So for today, I want to stop here, and thank you all for your attention.
Thank you. Thank you very much for this great talk.
Thank you.
Are there any questions from the audience? I am looking at the Q&A. Anybody has any questions about the talk? I have several questions before, unless. So my main question is, if there's no question from the audience, so the trick of absorbing the common noise term with a, I mean, basically, I think I have the impression that, I mean, the main trick is to remove the common noise term by choosing the test functions appropriately in a sense which is compatible with the transport equation, right?
Correct. Yes.
The main question is, I mean, so if small gamma was constant, for example, I think that will be obvious. You could see that essentially you should move everything with WT and then it will disappear.
Correct.
In your more complicated context, why the introduction of one psi allows you to remove this common noise term?
Well, yeah, so kind of in a nutshell, basically what you're doing, so let's look at the SPDE here, for example, right? So what you're doing, you're just forgetting about the drift part first, right? And you're just using the method of characteristics to solve the transport equation that is left, right? And so the point is that if you somehow take some nice test function and you follow it along the characteristics of this equation, you will you will precisely kind of absorb the common noise term, as you say. So it's sort of yes.
Why are you able to parameterize this absorption with only one parameter? That's my question. I mean, essentially, in this, your UTX is unknown, right? So I don't know which direction I should be going. What is the feature that makes that by only introducing one psi,
right,
I don't know which direction to take?
Yeah, so basically, so psi plays the role of u, right? So essentially, if you know, so if you know u, you know what coefficient you have in front of w, and that tells you where to move, right? So basically, yeah, how much of an increment of w to take.
So capital G only depends on u. That is the main reason.
Exactly. Yeah.
If you have something more general, you might need to introduce more, I mean, something.
Exactly. So the key point is that you have something purely rank based here, so that the coefficients depend only on you. Yeah, that's exactly right.
I see. Okay. So I mean, yeah, I mean, it is somewhat related to something we did with Erhan. In that case, there was only one direction, so you could just absorb it. Here, there are many directions, and yeah, you can parameterize all the directions that you need with the level of u. I see.
Exactly. And so, I mean, this extra thing with B just says that, I mean, sort of for convenience, we're absorbing the T as well, right? Because the BX dt term we can think of as just a similar term, right? Where the driving path is T. And so similarly, you know, my comment about several common noises. So if you have several W's with some different coefficients of u in front of them, you can use exactly the same trick, right? So you will just add up all of these directions and move into kind of the aggregate direction. That's right.
I see. What if, I mean, for example, if, I mean, it's not an SPDE, but I mean, if you think about all UTX as having a forward dynamics for all values of x, and for example, if capital G was depending on UTX and UTX plus 1, do you think that we could do it with psi1, psi2, or does it get more complicated?
I think you might be able to do it, but I have to write it down, to be honest.
Okay.
Yeah, but it might be doable.
I see.